Okay, so I think last class we stopped here, like 3 SALCs. One of them was A1 type, which is basically the combination of all the 1s orbital and same phase, right? So therefore, they are going to be all positive. So if we do that, so that means one is A was this, then one is B, then one is C, right? And then result and all, when all of them are a plus combination, so that means I'm going to have a density something like this, right? So that is all plus combination, and if you operate all the symmetry operations on this for C3b point group, you will find out that all are going to give you the +1 character. You can try to do that, you will understand this. And now the psi1e, so I am having two of them. After orthogonalization, we got this. Now this one is going to be double of the 1s A, so that means I will have little bit more electron density here, and then minus 1s B minus 1s C, they are in the same phase, so that is going to be in the negative phase. So let me draw that in a different color, so that will, let's say that is, I'm going to put it in the blue. So this is 1s B, this is 1s C, right? Now when they are in the same phase, so that means they will have the build up combination between them. So resultant is going to be something like this, and what we get is now that if we look at here, there is a node along this, right? And this is kind of PX, kind of PX. It's not exactly PX because it's SLC, so it's kind of PX, right? Then if you go for the second one of E type, the 1s A, we don't have any contribution, right? Then we have 1s B, this one, and so that is positive, and this is 1s C is negative, right? So that means I'm going to have something like negative part, I'm going to have like this, and for positive part I'm going to have red color, so that is going to be this, right? So that is minus combination, so this is going to be plus and this is going to be minus, right? So resultant you can think about something like this is for positive one, and the blue is going to be for the negative one, so it's something like that, right? So this is kind of like a PY if you look at along this Y axis, so that is going to be PY. So these are the 3 SALCs where we ended up in the previous session. It's like that, right? Okay, now what we have to go for is that whatever is the type of symmetry these SLCs are, we have to combine them according to the symmetry of the atomic orbitals of the nitrogen. Okay, so let's check the atomic orbital of nitrogen and how they symmetrically span. Okay. Okay, now nitrogen atomic orbitals, we have like valence orbitals only, of course we are going to consider. So the valence orbital are going to be 2s, 2pz, and 2px and py. So these are px and py, they are doubly degenerate, so they go for change simultaneously, so that's why we have grouped them together. Okay, now if we go one by one, let's go for 2s. Now 2s I have not drawn it here. So nitrogen is going to be above the plane here. This is the 3 hydrogens. Nitrogen will be above the plane along the z axis. Right. Now if I take 2s being spherical, right, so whatever the operations we do, it should remain unchanged. Like if we do identity, that should be 1, 2s being spherical. Now if we do C3 along z, now this 2s orbital is sitting on the z axis, right? Because it is nitrogen 2s, nitrogen is sitting on the z axis. So if I do C3, that remains unchanged. So that is 1. Now sigma v xz again, if we take xz, this 2s is sitting on the z, and if I take xz plane, so this one, right, so that is going to be, take any plane, it will remain unchanged anyway, so that is going to be 1, right? So the irreducible representation, therefore it is going to be A1. Okay, now go for pz. So this is the pz I have drawn in such a way that you have to assume that this is z axis and is perpendicular to the plane of this screen, computer screen, right? So if we do this, now again red is plus, blue is minus, if you can think in that way, or it doesn't matter. Now pz, we perform identity of course 1, you don't have any doubt about that. Now I am doing C3 along z, right? Now C3 along z means it's perpendicular to this, and this is pz, of course, so I am giving rotation along z axis, so therefore pz remains unchanged, right? So that's why this character is going to be 1. Now again, if I do sigma v xz, right, so it contains basically a z axis, right? So therefore this is going to be also 1, xz plane. So this is again is going to be A1 irreducible representation. So totally symmetric. Both of them are going to be totally symmetric, right? Now if I go for px and py, right? So identity, of course, is not going to change, right? Identity, if I do, none of them are going to change. So let me just get those px and py. So let's say this is px and this is py, right? Of course, they are sitting in the same place on the nitrogen atom. Now, if I do identity, they remain unchanged, right? So therefore, the character is going to be 2, 1 for this, 1 for this. So total is going to be 2, right? Now, when you go for C3, look at here. So I'm performing C3. When you do C3, see how both of them are going to change the orientation. Now, once we give C3 means 120, it goes like that, and this is also 120. It is like that. Now look at here. If you compare to see, this one is along x, this one is along y. So this can be written in independently on px and independently on py. But when you do C3 operation on both of them, what we get is that now this is oriented like this. So now this one can be written in terms of the x component and y component of the old coordinates, right? So therefore, this is not really independent. Similarly, this also, if you look at here, this cannot be independently written in terms of either px or py. So this will be the combination of old x and old y. So therefore, they transform simultaneously. Now, the simplest way to get the character, so this is 120 rotation. So cos 120 will be the character contribution for each of them. So cos 120 is minus half for this, and this is also going to be minus half. So therefore, I'm going to get character minus 1. Right. So that is going to be -1 for Px and Py. That's why they are doubly degenerate and transform simultaneously. Right? Now, if I go for sigma Vxz, now look at it. If I go for xz, this plane, xz plane, if I take, then Px remains unchanged. Right? Now, Ey, of course, if I take xz along this, is going to go to minus Py. So therefore, plus 1 from this one, when I go for sigma Vxz, this one, and then it is going to be minus 1 from this one, right? So therefore, resultant is going to be 0, right? So now if you look at this character table, then you can find out this is going to be doubly degenerate representation E. Okay. So what do we get? We get valence orbitals of a nitrogen atom, 2s, 2pz, both of them are totally symmetric. So A1, A1. And Px, Py, they transform simultaneously. We get doubly degenerate represented E. Now that we can, we have this irreducible representation, we have to combine this with the same symmetry, corresponding same symmetry of the SALCs. Right? So that's what we are going to do it now. So if we come to this, what we really, here actually I have just listed those SALCs of different types and the atomic orbitals of nitrogen of different types. Like A1, my SALC was this combination, all positive combination, 1 by square root of 3. Now, for nitrogen, I'm having 2s and 2pz. So when I form the molecular orbital, because they belong to the same symmetry, I have to take the linear combination of all these three. So this is A1 type, and then 2s, 2pz. So I will be forming the molecular orbital of A1 type, taking linear combination of this, C1 into this, plus C2 into this, plus C3 into this, A2pz. Right? Then exactly the way we have discussed, like previous molecule, like water molecule, we are going to get 3 MOs using from 1 SALC and 2 atomic orbitals. So resultant we are going to give you the 3 MO. Right? So that we will see how it is going to look like. They are going to look like. Now for E type, I am having 2 of the SALCs. One of the is this 2 into 1 is A minus 1 is B minus 1 is C. So that is along kind of PX. So that's why I have written PX here. So I can combine 2 PX with this only, not this one. Right? That will not give you the combination, because they are not same type. Right? Although they belong to identity, but their diffuseness is going to be different. So the 2-3 things you have to remember. First thing is that they should belong to the same symmetry, right? Here they belong to the same symmetry. Second thing is that their energy have to be comparable. And third is also the diffuseness, how they are diffused. Like that's why we normally don't go combine with the 1s orbital with the 2p, right? So that is the reason like this. Anyway, so this looks like to px. So therefore, I'm going to combine with this 2px. Now this looks like, that's why I gave the shape of this beforehand, such that we don't get confused. This looks like to py. So therefore, I'm going to combine with the atomic orbital of 2py of nitrogen. Right. So that is the way we should combine. Right. So what then I combine? So that means when I go for the molecular orbital of A1 type, right? So I'm going to get 3 of them, and that is going to be, of course, like is going to be something like combination of C1 psi A1 type plus C2, 2s of nitrogen plus C3, 2pz. Right. So if we take linear combination and then we form the secular equation, right, and or the Slater determinant, secular determinant, sorry, this determinant we form using this coefficient, we get 3 by 3 determinant, right? Now from 3 by 3 determinant, when we solve for non-trivial solution, we are going to get coefficient C1, C2 and C3. Now according to their value, when we combine, we are going to get 3 MOs, right? So those 3 MOs we are going to plot it. Exactly in the same fashion, we have to do it for the doubly degenerate representation. So one of the combination of what I am going to take, this one plus this one. So let's say this is going to be so E type. Okay, now one thing you have to remember, when I'm going for MO, I'm writing small letters, because this is the convention. These are symmetry species, we write in capital, and when you go for MO notation, you go for the small notation. So but that is just a notation, it has nothing special about it. So we have to go for simultaneously for E, right? So in that case, I'm going to have this one plus this one, and the second one is going to be, so this is one type, is going to be, let's say C4. Then I'm going to have psi 1 E type plus C5 2px. Okay, similarly I will have another one. So if you want, you can give E1, E2, but it's not, because they are degenerate. So we really don't need to go for separate one. So this one will give the combination of this and this. So I'll have two of them, molecular orbital. Similarly, I'll have this one and this one combination. So that is going to be C6 and C7. So I'm not writing that, but anyway, so this is the way we do. And then when we from the secular determinant and solve it, we get all the coefficients. Now, how these are going to be combined pictorially, that is more important, and we are going to discuss that. Okay, so look at here, I have arranged like this. So these are nitrogen atomic orbitals. This is 2s A1 type, it's lower in energy than 2pz, 2px and 2py. 2pz A1 and 2px, 2py are doubly degenerate, right? So that's like that. Now right hand side, I'm having 3 hydrogen atoms, atomic orbitals. When you combine, so that is 1s, 1s, 1s. So just for separation, we have done 1s A, 1s B, 1s C. Now when we make their SALC, we get 3 of them. This is going to be A1 type, so all positive combination. Just look at it, the contour. And the other 2 are going to be E type. So this is going to be kind of PX. That the way we have considered. I just want to mention here is that the A.K. Chandra book, they have he has done it the coordinate system in a little bit different way. So don't get confused, right? You choose whatever you want to take the coordinate properly, and you have to mention it, but answer you should get the same. So this is kind of going like a PX, and this is PY, so they are doubly degenerate, right? So like this. So this is the A1, these are doubly degenerate. Now when you combine the combination, we have to look for the symmetry of A1 type orbital. So I'm having this 2s, this SLC, and 2pz, right? So when you combine them, we're going to get the molecular orbital. So I'm writing like this. So one A1 is going to be, let's say, here, right? So that is the one. Now this one, you can understand that this is mostly going to be contributed, like coefficients for 2s and this A1 type is going to be dominating. Maximum contribution will be from here, then here, and 2pz almost there is no contribution. So that is will be very small contribution. So what I'm going to do is that I'm going to connect this and connect this for the timing to get this one. Right, I'm going to get 3 of the A1. The second one is going to be somewhere here. Now this combination is going to be like mostly from this 2pz and this one and 2pz, right? This will not have that much contribution, but if you wish, you can of course connect this. So this will have small contribution, so it is going to be like this. So this one, the second A1 is going to have the combination of these 3, and the third one, of course, is going to be anti-bonding type. This is going to be kind of non-bonding. Yes, this is kind of non-bonding orbital like PZ. I'll show you how it comes. Now the other one is going to be combination of this and this with negative combination. So that is kind of anti-bonding, and that is going to be somewhere here, let's say. Right, so that is another A1. So to make it separate, this is 1A1, this is 2A1, and this is 3A1. Okay, and that combination is going to be this minus this. So that means minus part will be somewhere in the middle, and again it's going to be up. When you have the plus combination, then this plus is going to be combined with this plus, and we have very small negative one, so that is different one. Now the negative one is going to just flip around this, flip this with the negative in the towards below along Z, right? So then you will understand how this would look like. Okay, now this one is going to be mostly connected with this, mostly contribution you are going to have from PZ and this. Okay, no contribution. No, I should not say no contribution, or the contribution is so negligible that I really don't connect it. Okay, now I'm having doubly degenerate E here and E here. So if I combine them, so PX, look at here, PX is going to combine with this, which looks like PX. When I'm having plus combination, then I'm going to have this energy somewhere here. So that is 1. Now anti-bonding, when I go this minus this, so this flips around, right? So I'm going to have a combination where it's going to have this is plus, this is minus, but when you go minus combination, then it is flipping around, this is minus, this is plus, right? So that is going to have the shape. So anyway, let's say I'm going to put it here, right? So that is kind of this anti-bonding, one of them, so that is this one, then this is going to be this one. Sorry, I could have done it a little bit later, but anyway, and kind of like this. Okay, so let me erase this because I have to draw one more. Yeah, so let me put it something like here. Right, so this is the connection between this. So PX and this. Now when you go for PY, and this. You can look at here again, if we go for plus combination, so this is plus, this is minus, this is plus, this is minus, so we'll have the second one here, right? And the other one is also going to be anti-bonding minus combination is going to be there, right? So these are basically E type. So one E here, and then 2E is going to be there, right? These are doubly degenerate. So first combination is from PX with this, second combination of PY with this. So all are going to have the both. When we have the plus combination, both of them are having same energy. Energy level is here. When both of them negative combination, they are here. So that is doubly degenerate. Okay. So now I have done the calculation in the computer just to give you the feeling how they should look like. Let's see how they are going to see in the molecular orbital picture. Okay, so this energy level are a little bit shifted, but you can look at here. This is basically combination of all these plus and this maximum contribution. PZ almost is not there, so it looks like all positive. So maroon color is basically plus combination for positive. Now when you go for this one, you can look at here. This is mainly contribution of this and this. So as if like when you go for combination with this, so then I'm going to have plus this one and then minus this one with this, right? So that's minus combination going to look like that. So that is basically it's more size is more because a plus combination is going to get like plus in one side and then we are having minus in another side, right? That is plus combination of, you can think about this and this. So plus lobe of this is going to combine with this and minus is going to be above that, right? So that is kind of it's not PZ exactly, but kind of PZ, and energy is very close to this. So that is quite more like a non-bonding of A1 type. Okay. Now this one is little bit more difficult to visualize. It's just a combination of this minus this. So that means plus lobe, if you flip it around, minus lobe is going to towards this. So there will be negative in between and then again a positive. So that's what you can see here from like very small maroon color which gives the positive, and that's why it's very difficult to anticipate without doing the calculation. Anyway, so but don't worry about this for the time. Okay, now if we go for the doubly degenerate this PX, look at here, this PX, if I take this and this plus combination, so this is plus, so we are going to have plus here, and the bottom is diffused one, so that's why this bottom is also more diffused compared to plus sign. Right. Now this one is for PY. Can look at here, it's as if like almost PY, and this is PY, so that will be more like a regular PY. So plus is going to be this plus this, and minus is going to be this and this. So that is like they are fun, they are doubly degenerate. Now when go for minus combination, again this is a little bit tricky. So we have this minus this, so that means I'm going to have a small minus there, and then is going to be again this is negative more and then plus here. So that's what you are going to look at here in this picture. The other one is very easy to visualize. We go for minus combination this and this. So let me draw it, then you can. So this is plus, and then if I go for minus combination, that means that this is going to be plus, and the other side is going to be, I'm having minus, right? So this is plus, this is minus, again this is plus, this is minus. So that is kind of look at here. So you can think about this is plus, Again, this is minus, this is minus, this is plus, so it's kind of shape what we are going to look at it. Right. So that's what it gives you the idea about the molecular orbital of MO. Right. Okay, now let us put the valence electrons. How many electrons do we have? So 2s, I'm having 2 electrons. Then how many electrons I am having? This is 1, this is 1 electron, and so I have 5 electrons for the nitrogen, the valence orbital. Then I am having 3 electrons from 3 hydrogen, so 2 of them will be here and 1 of them going to go there, either of them. Right. So therefore, if we fill it up, so I'm going to have W occupied this, W occupied this, W occupied this, and then also W occupied this. Right. So you can understand now that you can think about that this is kind of non-bonding, and it's basically lone pair of the nitrogen you can think about. Right. So that's what is the electron density we get more on the nitrogen atom for the lone pair. Right. So this is what the molecular orbital what we get. Now again, as I discussed in the in case of water molecule, this is HOMO, highest occupied molecular orbital, right? HO, capital M, HOMO, and this is LUMO. Right. Now, if you are looking for the transition from HOMO to LUMO, you have to go for the direct product representation. So that means the way we have done it for UVIR also, here also we have to go for like this. So A1, 2 into A1, right? So that is going to be A1. This is A1, and then we have dipole moment, and you will realize that dipole moment goes along X, Y, Z. So if Z is going to be A1, so that may be transition may be feasible. So like that. So that is electronic transition. We'll do it in a different way, but that is the way we apply the symmetry. So the question is whether this transition is allowed or not. So that's what we discussed, and that gives you the idea how the spectroscopy of the molecules goes like this. Okay, so that is all about what I wanted to discuss about the ammonia, and of course C2B already we have done for water, C3B ammonia, and I'd like to stop here for this SALC. Okay, now before I close this, I would like to give you the I'd like to see if you are able to do it, your home assignment. So that is this was in your home assignment, like form SALCs for pi orbitals of cyclopropenyl group using 3px orbital on each carbon atom as a basis. Right? I hope you'll be able to do it, and some of you have already done it. I have seen your home assignment copies, but I could not complete it, so I'm going very slow. Okay, so now just for the pictorially, how do you do it? This is the cyclopropenyl group, and you have P, this 3P. Now you have to think about is that Z axis is going through the center and it's like this. So that is along Z. So therefore, pi orbitals of these are going to be formed by the PZ. So these are all PZ, 3 PZ, right? And they are going to form the pi orbitals. So of course, what you have to do is using these PZ orbitals as basis, you have to form different types of SALCs, right? So that is the home assignment I had given, and now you give a try again after this discussion. I hope you will be feeling more comfortable to do it now. except that I'm giving you a little bit more complicacy that other than C3b. Right? C3b was relatively much easier compared to this, because point group of is going this is going to be D3H, because this is going along C3, this principal axis. Then you are going to have horizontal plane, right? And then you have C2 also. These are 3 perpendicular C2s, right? So that is D3H molecular point group, and you will have little bit more involved when you do the SALC's index, right? Okay, so with that, I would like to stop here, and then when we reconnect it, we'll have the discussion and see how it goes. Okay, so let me stop sharing here.